Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to the 8th lecture of Mechanics of Solids. We started the discussion on axial loads in the previous lecture. In this lecture, we are continuing with that discussion. In this lecture, we are going to discuss the fundamental principle of superposition that allows us to consider the cumulative effects of multiple loads acting on the body simultaneously. The second concept in this lecture is the statically indeterminate axially loaded members. Third concept is the thermal stresses. And finally, we'll end this lecture with a discussion on the stress concentrations. The principle of superposition is often used to determine the stress or displacement at a point in a member when the member is subjected to a complicated loading. By subdividing the loading into components, the principle of superposition states that the resultant stress or displacement at the point can be determined by algebraically summing the stress or displacement caused by each load component applied separately to the member. The following two conditions must be satisfied before application of this principle. The loading must be linearly related to the stress or displacement that is to be determined. For example, in the case of axially loaded members, we are having the equation for the axially loaded stress and the displacement, which we considered in the previous lecture, and you can refer to that lecture for clarification. The second condition that must be satisfied is that the loading must not significantly change the original geometry or configuration of the member. If significant changes do occur, the direction and location of the applied forces and their moment arms will change. For example, consider the slender rod in this figure. It is under the application of this load P. If we replace this P by two components, P1 and P2, if P causes the rod to deflect a large amount, the moment of the load about its support, PD, will not be equal to the sum of the moments of its components loads, P1 into D1 plus P2 into D2. I hope this principle is clear because it will be used throughout this lecture as well as in almost all the concepts of almost all the basic concepts of mechanics of solids, where we assume that Hooke's law apply and also the bodies that are considered will be such that the loading will produce deformations that are so small that the change in position and direction of the loading will be insignificant and can be neglected. Now we are going to discuss the statically indeterminate axially loaded member. In order to understand statically indeterminate axially loaded member, let's consider this bar. If we write an equilibrium equation for this bar by considering the forces that are applied at the supports and this applied load, we'll come to know that this equilibrium equation is not sufficient to determine the two unknowns because we are having only one equation and we have two unknowns FA and FB. Thus, we need another equation to determine these unknowns. How can we determine that equation? That is determined using compatibility or kinematic condition. This means that in order to establish an additional equation for solution, it is necessary to consider how points on the bar displace. In this case, a suitable compatibility condition would require the displacement of one end of the bar with respect to the other end to be equal to 0 since the end supports are fixed. Hence, the compatibility condition will be the displacement of end A with respect to end B is equal to 0. Now, we can express this equation in terms of the loads by using the load displacement relationship discussed in the previous lecture, which specifically depends on the material behavior. Like we have this relation delta is equal to PL by AE, and we can notice here that if we consider this segment AC, then the load at this end of AC is FA and the load at the end of CB is FB. And this FA and FB will be in the opposite directions. So now this equation, this compatibility equation can be written as, like, we basically were having del A minus del B is equal to 0. So by replacing del A by this equation and del B by this relation, and assuming that AE is constant, we have arrived with this equation FA is equal to FB into so on. Now using the equilibrium, we are having the relation for FA and FB. Thus, in the statically indeterminate members, in addition to the equilibrium condition, we also need to satisfy and write an equation for the compatibility or kinematic condition in order to solve these members. Let's summarize the procedure for analysis of statically indeterminate axially loaded member. First of all, the support reaction for statically indeterminate members can be determined by satisfying equilibrium, compatibility, and force displacement requirements for the member. For equilibrium, we have to draw a free body diagram of the member in order to identify all the forces that act on it. Then the problem can be classified as statically indeterminate if the number of unknown reactions on the free body diagram is greater than the number of available equations of equilibrium. Then we have to write the equations of equilibrium for the member. After that, if the member is statically indeterminate, then we also need to satisfy or determine the compatibility conditions. For this we have to draw a displacement diagram in order to investigate the way the member will elongate or contract when subjected to the external loads. Then we have to express the compatibility conditions in terms of the displacements caused by the loading. Then we have to use a load displacement relation such as delta is equal to PL by AE to relate the unknown displacements to the reactions. Then we have to solve the equilibrium and compatibility equations for the reaction. If any of the results has a negative numerical value, it indicates that this force acts in the opposite sense of direction to that indicated on the free body diagram. This is our first example in which we are having a steel rod of diameter 10 millimeter. It is fixed supported on both of its ends, and before it is loaded there is a gap of 0.2 millimeter between the wall at B dash and the rod. Determine the reaction. We have to determine the reactions at A and B dash if the rod is subjected to an axial force of 20 kilonewton. We can neglect the size of the collar at C, and we have to take the modulus of elasticity of steel as 200 gigapascals. Sorry, this P should be capital. This is a mistake in this. Okay, first of all, we have to satisfy the equilibrium, or we have to write the equilibrium equations. We need to only write the summation of forces in the x direction. This we usually take the right hand forces or the forces directed towards right as positive. Thus, FA and FB are indicated as negative here, and this load of 20 kilonewton is positive. We can see here that the equilibrium alone cannot provide us with the with enough equations to get the two unknowns, so we need compatibility in addition to equilibrium. For compatibility, we know that the force P causes point B to move to B dash with no further displacement. Therefore, the compatibility condition for the rod is simply the change in displacement of point B with respect to point A is 0.0002 meters. That displacement shown in the previous slide can be expressed in terms of the unknown reactions using the load displacement relationships. As shown in this figure, again as in the previous example, this FA will be equal to minus FB, and if we are expressing these loads in terms of the displacements, we can obtain this particular equation. Now we are having by solving these equations, we are having two equations and two unknowns, and solving simultaneously the equation 1 shown in the previous slide and this equation 2, we have obtained this FA and FB as equal to 16 kilonewton and 4.05 kilonewton respectively. Since the answer for FB is positive, it means that NB contracts the wall at B dash as originally assumed. Okay, in the second example, we are having three A36 steel bars which are pin connected to a rigid member. If the applied load on the member is 15 kilonewton, then we need to determine the force developed in each bar. Bars A, B, and E, F have a cross-sectional area of 15 millimeter square, and bar C, D has a cross-sectional area of 30 millimeter square. Again, first of all, we'll write the equilibrium equation. We are having two equilibrium equations in this problem. First of all, we'll write it for the summation of forces in the y direction, and for summation of forces in y direction, we have this equation: Fa plus Fc plus Fe minus 15 is equal to 0. And for the summation of moments, we are having this equation in which minus Fa, or since we are taking the anti-clockwise as positive, and this Fa will cause a clockwise moment with respect to this point C, and Fe will cause an anti-clockwise moment with respect to point C. So the moment due to Fa will be negative, the moment due to Fe will be positive, and the moment due to this 15 kilonewton is also anti-clockwise here like this. So this moment is also taken as positive, and the summation of all these moments is equal to 0, obviously. How can we determine the compatibility in this case? For this, consider this thing that the applied load will cause the horizontal bar ACE to move to the inclined line A dash C dash E dash. The displacements of point A, C, and E can be related by similar triangles, like we are having this triangle A dash, this point E dash, and this is then similar to this triangle C dash, this point, and then E dash. Thus the compatibility equation that relates three displacements is del A minus del E, this is del E, divided by this point 8 is equal to del C dash, del C, displacement of this point C, minus displacement of point E, divided by zero point 0.4. Thus, we have obtained this using the load displacement relation. Obviously, we can replace this del C, del A, and del E by their respective load displacement relationships, and thus we have obtained the third equation. And now we are having three equations and three unknowns, and we can solve these three equations simultaneously to obtain these three unknown forces in the three bars. We are moving towards another type of axial loading, that is the thermal stresses. A change in temperature can cause a body to change in dimensions. Generally, if the temperature increases, the body will expand, whereas if the temperature decreases, it will contract. Ordinarily, this expansion or contraction is linearly related to the temperature increase or decrease that occurs. If this is the case and the material is homogeneous and isotropic, it has been found from experiments that the displacement of a member having a length L can be calculated using the formula delta T is equal to alpha into delta T into L, where this del T is basically the algebraic change in the length of the member. Alpha is a property of the material referred to as the linear coefficient of thermal expansion. The units measure strain per degree of temperature. They are usually per degree Fahrenheit or per degree Celsius or per degree Kelvin. This delta T is the algebraic change in temperature of the member, and L is the original length of the member. The change in length of a statically determinate member can easily be calculated using this equation shown. However, in statically indeterminate members, these thermal displacements will be considered by the supports, thereby producing thermal stresses that must be considered in design. Like in statically indeterminate members, due to the constraint on the at the location of the supports, these thermal displacements will result in thermal stresses. Determining these thermal stresses is possible using the methods which we have discussed in the previous slides, like like establishing compatibility and all that. And we'll illustrate the application of these methods in the upcoming examples. The A36 steel bar shown in figure is constrained to just fit between two fixed supports when T1 is equal to 60 degrees Fahrenheit is the temperature. If the temperature is raised to T2 is equal to 120 degrees Fahrenheit, we need to determine the average normal thermal stress that is developed in the bar. Again, we are having this basic equation summation of Fy is equal to 0. Since there is no external load, the force at A is equal to the force at B, but it will be in the opposite direction. That is, Fa is equal to Fb is equal to F simply. We have determined from the equilibrium that this problem is statically indeterminate because the unknown force cannot be determined solely from the equilibrium condition. Thus, we need to establish the compatibility condition. The displacement at point A with respect to the point B will be 0 because the bar is fixed supported. The thermal displacement at A that occurs is counteracted by the force F that is required to push the bar back to its original position. Like this thermal displacement will try to occur, but then we are having a force here, so it will be counteracted, it will be pushed back to its original position. The sum of these two displacements will be equal to 0. The compatibility condition at A then becomes del AB is equal to 0, and then the summation of these two equal displacements will also be equal to 0. And if we replace the thermal displacement by the respective equation and this displacement due to the force F by its respective value, we'll come up with this equation. Now we can use the data to determine F. Because we are having all these values, we can determine F from this equation. Since F also represents the internal axial force within the bar, the average normal compressive stress is thus, this will be the value of the compressive stress throughout the whole bar. This is a little bit more complicated example than the previous one because in addition to temperature changes, we are also having an external load here. And now we will see the application of principle of superposition for two different kinds of loading as well. Like both these loading are axial, but the nature of these loadings is different. The rigid beam shown in the figure is fixed to the top of the three posts made of A36 steel and 2014 or 2014 T6 aluminium. The posts each have a length of 250 mm when no load is applied to the beam and the temperature is 20 degrees centigrade. Determine the force supported by each post if the bar is subjected to a uniformly distributed load of 150 kilonewton per meter, and the temperature is raised to T2 is equal to 80 degrees centigrade. Now for equilibrium, we have this summation of forces in the y direction to FST, because we are having two steel rods plus the force in aluminium must be equal to the force that is being applied here at the top. This 150 kilonewton per meter has been turned into a concentrated force, this distributed force, by multiplying it with the length of this uh, rigid beam. Thus we have 90 into 10 raised to power 3. Now we also need one compatibility condition, because we are having again two unknowns and one equation. Let's see how we'll obtain that compatibility condition in the next slide. Now, um, due to the load, geometry, and material symmetry, the top of each force is displaced by equal amount. This means that the displacement in the steel bars will be equal to the displacement in the aluminium. We can see here that del St is equal to del aluminium, and the displacement in the steel as well as in the aluminium will actually be equal to the summation of the displacements due to temperature as well as the displacement due to the loads. Thus, we have written here equations in terms of the steel and aluminium, and then we can put these equations in this equation too. Now we are having two equations and two unknowns, and again we can use any method for the simultaneous equations to determine the force in the steel as well as the aluminium. To be consistent, all numerical data has been expressed in terms of newtons, meter, and degrees Celsius. The negative value for the FST indicates that this force acts opposite to the to our originally assumed direction of the upward force. In other words, the steel posts are in tension and the aluminium post is in compression. Now we have come to the point of discussing a very important topic in the stresses, that is known as the stress concentrations. It is an important topic because most of the failure in the material occurs at the location of the stress concentrations. Now, why do those stress concentrations occur and how can we consider them in design? We'll just get to know these things in the coming slides. It was pointed out in the previous lecture that when an axial force is applied to a member, it creates a complex stress distribution within the localized region of the point of load application. Not only do complex stress distribution arise just under a concentrated loading, they can also arise at sections where the member's cross-sectional area changes. For example, consider this bar, which is subjected to an axial force P. Here, the once horizontal and vertical grid lines deflect into an irregular pattern around the hole centered in the bar. The maximum normal stress in the bar occurs on section AA, which is taken through the bar's smallest cross-sectional area. Provided the material behaves in a linear elastic manner, the stress distribution acting on this section can be determined either from a mathematical analysis using the theory of elasticity or experimentally by measuring the strain normal to the section AA and then calculating the stress using Hooke's law simply as sigma is equal to E into strain. Regardless of the method used, the general shape of the stress distribution will be like that shown in this figure. In a similar manner, if the bar has a reduction in its cross section achieved using shoulder fillets, as in this figure, we are having fillets here, then again the maximum normal stress in the bar will occur at the smallest cross section area, section AA, and the stress distribution will again look like this form. So we can see here that the stress distribution, or the stresses increase near this discontinuity or near this change in cross-sectional area. This is very self-evident because stress is inversely related to area, and if area is decreasing, then automatically the stress will be increased in that particular location. However, we need to determine how can we consider this change or this increase in stress in our design. In both of these cases, force equilibrium requires that the magnitude of the resultant force developed by the stress distribution should be equal to the applied load P. In other words, P should be equal to the stress over this whole area, or the integration of the stress over this whole area. This integral graphically represents the total volume under each of the stress distribution diagram. If this is the stress distribution diagram, then uh, the total volume under the stress distribution diagram is basically represented by this integral. The resultant P must act through the centroid of each volume. The actual stress distribution shown in this figure or in this figure do not have to be determined for the engineering practice. Instead, only the maximum stress at these sections must be known, and the member is then designed to resist this stress when the axial load P is applied. Specific values of this maximum normal stress can be determined by experimental methods or by advanced mathematical techniques. The result of these investigations are usually reported in graphical form using the stress concentration factor K. We define K as the ratio of the maximum stress to the average normal stress acting at the cross section. If we know K and the average normal stress that has been calculated from simply this P divided by cross sectional area of that section, where A is the smallest cross sectional area, then the maximum normal stress can be calculated as K into P by A. This is a concept basically from fracture mechanics, that we determine K using experiment, and then we determine this maximum stress at any location by using this particular equation. Specific values of K are generally reported in handbooks, for example codes, etc. These two graphs show some of the experimentally determined values of the K, and we can correlate this K with the respect to the geometry and the type of the discontinuity. It should be noted that K does not depend on the bar's material properties, it is only dependent on the bar geometry and the type of discontinuity. As the size R of the discontinuity is decreased, the stress concentration is increased. For example, if a bar requires a change in cross section, it has been determined that a sharp corner produces a stress concentration factor greater than 3. In other words, the maximum normal stress will be 3 times greater than the average normal stress on the smallest cross section. However, this can be reduced to say 1.5 by introducing a fillet. A further reduction can be made by means of small grooves or holes placed at the transition. In all of these cases, these designs help to reduce the rigidity of the material surrounding the corners, so that both the strain and the stress are more evenly spread throughout the bar. The end of our lecture. In summary, we discussed four main topics in this lecture. The first one was superposition. Superposition of load and displacement is possible provided the material remains linear elastic and no significant changes in the geometry of the member occur after loading. The reactions on a statically indeterminate bar can be determined using the equilibrium equations and compatibility conditions that specify the displacement at the supports. A change in temperature can cause a member made of homogeneous isotropic material to change its length if the member is confined. This change will produce thermal stress in the member. Holes and sharp transitions at a cross-section will create stress concentration. For the design of a member made of brittle material, one obtains the stress concentration factor K from a graph which has been determined from the experiment. This value is then multiplied by the average stress to obtain the maximum stress at the cross-section. Stress concentrations are also responsible for many failures of structural members or mechanical elements subjected to fatigue loadings. For these cases, a stress concentration will cause the material to crack if the stress exceeds the material's endurance limit, whether or not the material is ductile or brittle. However, the material localized at the tip of the crack remains in a brittle state, and so the crack continues to grow, leading to a progressive fracture. As a result, one must seek ways to limit the amount of damage that can be caused by fatigue. Thank you for listening to this lecture. I'll be happy to answer your questions.